In this video, I will introduce a theorem for sufficient statistics. In the last video, we went over the formal definition of sufficient statistics, and we used the definition to prove that the sum of random variable xi is actually a sufficient statistics for Bernoulli distribution. What does this theorem say? Imagining we have fxx to be the joint distribution of x. Just to be clear, this actually means that x1 is equal to x1, x2 is equal to x2, xn is equal to xn. That's what it means when they say this is a joint distribution. And we also have qt, which is a PDF of t of x. Then the theorem says tx is a sufficient statistics for theta if for every x that comes from the sample space, the ratio of the joint distribution and the PDF of the statistic is a constant function of theta. What does it mean when they say it's a constant function? When you look at the distribution, there's no theta involved in the final result. That's what it means when they say it's a constant as a function of theta. But you can include x or even other parameters that are not theta in this ratio. You can still call t of x as a sufficient statistic. So let's look at the proof of this theorem. The theorem says the probability of x conditional on the distribution of t of x is a constant, is independent of theta. That's the definition. So let's further expand this. We know in the numerator, we have this joint distribution. And then by the definition of conditional distribution, the denominator is just going to be the marginal of the statistic. And again, we're going to see two scenarios. The first scenario is when t of x is indeed t. So the x right here and this x, they're the same x. That's why if t of x is indeed t, then x is naturally equal to x, since they are the same x. By saying that, I'm trying to show you guys the probability of x equal to x is equal to the probability of x equal to x jointly with tx equal to t. However, if t of x is not equal to t, then there's no way that this joint distribution is zero when one element of the joint is not going to happen. Yeah, don't forget the denominator here. And the denominator, what is the denominator? Remember, in the theorem, we define the distribution of t of x to be qt, so we can substitute this marginal distribution by qt. Similarly, we also define the joint distribution to be fx. So that's why we can substitute the probability of x equal to x to be fx. And similarly, we have the two conditions. Again, it's easy to see that this quantity right here is the same as the ratio. By the definition, we claim that when the probability of x given t of x is a constant function of theta, then we claim t of x is a sufficient statistic. So it's equivalent of saying this when this ratio is a constant function of theta, then we can say t of x is a sufficient statistic. Why is the theorem so useful? If you look at the result right here, when t of x is not equal to t, you always have 0, which is definitely a constant of theta. So that's why you don't even need to examine this scenario since it's always a constant of 0. All you need to worry about is whether this ratio is a function of theta or not. The theorem to show that a statistic is sufficient, you don't need to consider the separating cases when your t of x is equal to t and when your t of x is not equal to t. Let's look at one example together. It's the same example we did when we have x1 to xn. They're identical independent Bernoulli trial. And we want to again show that t of x equal to the sum of xi is a sufficient statistic for theta. So this time, we are going to write these two quantities separately and then take the ratio of them to check whether they are a constant function of theta or not. In this case, the theta we're interested in is p. So let's do the joint distribution, which is simply the product of each marginal, like we did before. And let's combine the p terms. So we will have p to the power of x1, xi from I to n. We basically sum up the exponents. Similarly, 1 minus b to the power of, since we have n 1 minus p, so we have n times 1 here, minus the sum of I equal to 1 all the way to n of xi. And we know that the sum of Bernoulli trials are binomial distribution with parameter n and p. That's why we can directly write out the distribution of t using the binomial PDF. Now let's take the ratio. So in the numerator, this is what we have. I'm basically copying down what I wrote before. In the denominator, we're going to do a little trick here. Because we know t is equal to the sum of xi, in order to cancel out these terms, it's better to substitute t for the sum of xi. You'll see why in a moment. Okay, now it's time to do the cancellation. Apparently these two terms, they cancel out each other, and these two terms, they cancel out each other. Because we substitute t as the sum of xi, so we know they are equal to each other. That's why we can simply cancel these two terms. And then what we left here is just 1 over n choose from sum of xi. And we can actually substitute sum of xi back as t of x. Is this ratio independent of theta? It's true that there's no p involved in the final ratio. So we can claim t of x is a sufficient statistic.